In electrostatics, a single point charge radiates a symmetrical electric field. Its strength decays at a rate of 1 over distance squared. Moving twice as far away reduces the field to a quarter of its original strength. We disrupt this symmetry by placing an equal but opposite negative charge near the first. This configuration, two equal and opposite charges separated by a distance denoted as 2a, defines an electric dipole. Calculating the sum of these charges results in a net charge of absolute zero. If the system has no net charge, the question arises, why doesn't its surrounding electric field completely disappear? The field survives because the two charges occupy different coordinates in space. Because they are physically separated, their opposing electric fields cannot perfectly cancel, leaving a residual, distinct field pattern. Rather than calculating the interactions of two separate charges point by point, physicists treat the dipole as a single unified entity. Redefine this entity using the dipole moment vector, p. By convention, this vector originates at the negative charge and points towards the positive charge. The magnitude of this vector is the product of the charge magnitude q and the separation distance 2a. At distances much larger than the internal separation of the charges, the individual identities of the positive and negative points become irrelevant. The dipole moment vector dictates the geometry of the surrounding electric field and determines how the system reacts to external forces. Defining the dipole moment collapses a two-body problem into a single predictive vector, allowing us to map its influence on the space. We begin by calculating the net electric field at a distant point P, located directly on the axis line passing through the two charges. The positive charge, being closer to point P, exerts a strong outward push, represented by a large vector arrow. The negative charge is further away. Its inward pull on point P is measurably weaker, creating a smaller opposing vector. Subtracting these opposing forces reveals the final net electric field vector at point P. This derivation results in the formula for the axial field. Note that the dipole moment P is the central variable in the numerator. On the axis, the net field vector is perfectly parallel to the dipole moment vector. Because the physically closer charge dominates the interaction, the resulting net field remains aligned with the dipole's internal orientation. We now shift to the equatorial plane, a perpendicular line cutting through the dipole center. Because point P is equidistant from both charges, the individual field vectors hitting this point have identical magnitudes. Resolving these vectors into components shows that the vertical element are in direct opposition. They cancel each other perfectly. The horizontal components, however, point in the same direction and add together to form the net field vector. This provides the formula for the equatorial field, which differs from the axial formula in two ways. First, the numerator is halved. At an identical distance, the equatorial field is exactly half as strong as the axial field. Second, the negative sign indicates that the net field here points in the direction opposite to the dipole moment vector. On the equatorial plane, the absolute symmetry of the system halves the dipole's overall power and reverses its alignment. Comparing the denominators of these equations to a standard point charge reveals a critical change in how the field behaves across space. While a point charge decays over distance squared, the dipole's field decays at a rate of distance cubed. This graph illustrates the difference. The field of a dipole collapses much more rapidly than that of a single charge. Because the positive and negative charges are in a state of near cancellation, their combined reach is severely diminished as the distance from the system increases. The dipole's zero net charge does not eliminate the field, but it restricts its influence to a small volume of space near the charges. The true physical utility of the dipole moment is seen when the system is placed within an external electric field. Consider a dipole placed at an angle within a uniform external field. The field exerts a force pushing the positive charge and pulling the negative charge in opposite directions. Because these opposing forces are equal, the net force is zero. The dipole does not translate through space. However, because the forces act at different points separated by the internal distance 2a, they create a mechanical couple. This generates torque, expressed as P cross E, which forces the dipole to rotate until it aligns with the external field. The dipole moment determines how polar molecules, such as water, orient and react to external forces in the real world.